Hey, so I got a question for you guys. So this course has been chosen to be part of this ABET analysis.
Everyone like that is ABET this week. What is this?
What is that for? so apparently maybe some of your other courses are involved.
All of them. Yeah, every one of them.
All of them?
So we get like our final project for every class.
A non
Yeah, so-
mandatory final project.
It's a non-mandatory final project to this named after. It's great.
Is it non-mandatory?
It's non-mandatory,
It's-
but it's mandatory.
Yeah.
They won't let you graduate if you don't do it.
Yeah, so this is just for the accreditation board assessment. So this normally isn't a part of the course, right? For example, if you had taken this course last semester, you wouldn't have encountered this type of thing. But it is needed, and so I just want to go over with you guys what's required for this course. So was this information given to you guys from your other courses? No? Okay, so let's look at it a little bit. And so, so what this organization does, it does this with many universities, right? So any university that has an accredited program in STEM typically has to go through this. There has been, I think, a couple of universities who are now opting out of it. For example, over at UC Berkeley, they decided not to do this any longer. And their reasoning for not getting involved is because they are like, they're realizing that engineering is becoming more interdisciplinary, so they need to have more freedom to do extra things and go different directions and have all these other courses that haven't yet been incorporated into the ABET standard. So they already know that because of that, they're going to have difficulty trying to uphold that standard, right? Because they want to do other things. Now, of course, if ABET does, allow for those kinds of things, then I'm pretty sure they would actually be okay with it. Okay, but anyway, that's what they're doing. But yeah, so this is for Auburn to stay accredited. So as you can see here, here are the courses, and there we are right here. Okay, so so basically, what they are trying to find out is they're looking at the students and trying to find out if they have the ability to identify a problem and formulate a problem, and then of course then solve a problem. Okay, so I cannot give you a problem for this. You guys have to come up with your own problem for this, okay? And it has to have certain type of characteristics for your problem. So let me see. Yeah, you guys haven't seen this before, so let's go through this a little bit. So, so right here it says, an ability to identify, formulate, and solve complex engineering problems by applying principles of engineering, science, and mathematics. Okay. So the instrument. The student must create a homework problem that incorporates material from the class. Okay. I'm not sure what this is right here. So this is probably, I think this is the Journal of Engineering Education. Yeah, so so there's a field. Have you guys heard of engineering education as a branch of STEM? No? Really? Yeah, so well actually it's not that old. It's relatively new. So basically there is an actual, people actually get a degree in engineering education. And basically, it's a field that merges psychology with engineering, and they try to find ways to improve the education of engineering. but it's not just engineering, it's all of STEM, mathematics, science, technology, things like that. Okay, so this assignment would occur in each of the 4 classes selected per program to assess this outcome. Okay, so I guess, yeah, we're actually listed in all, in all sections, so you wouldn't be able to avoid this. You need to identify a problem. So describe an engineering problem pertinent to the material under study. Why is a problem of interest? How does it pertain to the course material? Here, formulate a problem. Okay, and this right here, student creates a non-trivial problem using course material of sufficient rigor to satisfy, this is all relative, right? to satisfy other terms, engineering, science, math, in the outcome statement. To ensure the problem is complex, it must have multiple parts with no obvious solutions. Okay, so that's how they're defining complex. So when you guys come up with your problems, just make sure it satisfies these kinds of things so that the problem, the solution is not obvious, right? Like you know, you just can't have like apply Ohm's law, then you're done. Okay. What engineering assumptions must be made to solve the problem? And we've been making lots of assumptions dealing with these MOSFETs and BJTs. A huge amount of assumptions. So you would list your assumptions that you're making to solve the problem. Okay, then so identify, formulate, then solve the problem. So in a tutorial fashion, the student is to show the step-by-step solution process, including key assumptions. Okay, so this is just like doing homework if you had written out. You would show your assumptions. First you identify your problem, you formulate your solutions, and then when you show your solution, you have to base it on your assumptions you're making. And then do your solution in a tutorial type, step-by-step, and try to explain every step. At least steps that are not obvious, notate those kinds of things. And the solution should be neatly and logically presented and yield the correct answer. I have to grade these things. So, other considerations. Let's see here. Yeah, I think this is pretty clear on what you guys can do, and I can give you some hints or some examples of where you guys can start formulating your problem. So this right here is, they're giving some examples here. Where are we at? Oh, here. Okay, so here's 3700 analog electronics. Okay, outcome 1, the ability to identify, formulate, and solve complex engineering problems and apply principles in engineering science. Okay, yeah, so the same as above. So identify the problem. Okay, so here's an example. The student will design an amplifier for maximum undistorted output amplitude. Understanding high performance amplifier design is very useful for a wide variety of electronic components, for instance in cell phones, and so the problem is rather typical in an analog electronics course. And those are the kind of things that we've been dealing with, trying to, creating problems, are looking at problems that try to reduce the amount of distortion, maximize gain, things like that. So it's not asking you to design an entire cell phone, right? Just the, the amplifier component of the cell phone. And so we've been dealing with this a lot. We started with op amps, and as you can see today, we'll go back to op amps. So we started with op amps, went to look at transistors and how they can be used as amplifiers, and now we're combining those together, and now we're recreating these op amps. So formulate a problem. Here's an example. using a 2N3904 NPN transistor and a standard 4-resistor bias network, which we've been using lots of times. I'm not exactly sure what this type of transistor is, but it's probably some standard type of transistor. But you put that in a 4-resistor bias network powered by a single 12-volt battery. Design a common emitter amplifier with a maximum undistorted voltage amplitude for a 10 kilohertz sinusoidal input signal. The signal source has a 300 ohm source resistance, and an amplifier is to drive a 1 kilo ohm load. Your solution must indicate the gain as well as maximum input and output signal paths. Yeah, so so that looks like a small signal type of analysis kind of problem right there. Okay, this right here, what engineering assumptions must be made to solve the problem, if any? For example, some conditions may be relaxed for this level of design problem. Typically, after the level of design, the circuit would be simulated and optimized using a SPICE simulator. We haven't been doing SPICE in this class yet, but we can. Has anyone ever used SPICE before? Anyone? Oh, wow. Okay. Wait, who has not used SPICE? That's a better question. Anyone has not used SPICE? Okay, great. All right, so, and do you all have access, who does not have access to SPICE right now? You know you've used it. You're going like this.
I can get it.
Okay. Okay, all right, that's good. All right, yeah, so you can use SPICE if you want to, okay, that's fine. But when you have your solution, that needs to be written out, and it needs to be typed, not by hand, okay? Actually says that in here. Yeah, see, all equations must be created by a word processor, not handwritten. So, but yeah, if you want to use SPICE and have some grab some plots, that'd be great for this. And a good source for coming up with problems, they can be, for example, from the for example, the examples given to you in your book, right? Like remember that one example where they had, and it was also on the exam too, where you were asked to design a very simple signal generator, that type of thing. That's a non-trivial problem, I would say. And let's say for your problem, you could do it like this. Yeah, so in the exam, it was just, you were to give the schematic of that system, but maybe to make it more rigorous, what you would do is say, you would select your frequency, right? And how you would select those frequencies. So, you would have so you would have each component, you would choose your resistances and your capacitances of all your components. You would define the period of your oscillator. Even your low pass filter, you would also try to tailor that to what you're trying to get. So you could easily formulate a problem around that. But these examples, your book is loaded with all kinds of real, sort of like real world examples where the concepts in that section are applied, right? So you can start there and tweak it, right? I'm not talking about these little examples right here. I'm talking about things like, here's another one. Yeah, like this right here. Now this is an interesting one. This one right here is actually, there's a better worked out. Yeah, right here. Yeah, so this is pretty interesting. And I think on this example right here, they're really, there's lots of components here, but they're really analyzing this part right there, which is the limiting amplifier. And let me give you another example, if I can find one real quick. Humbucker for guitar pickups right here. So yeah, if you can apply it to, yeah, here's another one right here. 3-stage amplifier. And the nice things about, and I'm glad you guys are all familiar with Spice, because that will make it a little more easier to check your answers, because it did say you would like your answers to be correct. And so what you could always do is validate or verify your answers by looking at, comparing your analytical results with your computer results in Spice. Yeah. So, but again, complexity is all relative, okay? And you guys can choose your own type of problem you want to look at. You don't want to make it too complex, right? But just make it not obvious according to their definition of what complexity is, okay? Here's something else they sent me too. This right here, student accountability. Oh, I think this is like a rubric type of thing. And so, okay, so what this looks like is this. So this is a rubric. This part right here is how well you have identified a problem. So that's the row here. How well you formulated is this part, and how well you solved is this part. And then each of the columns right here is if it's unsatisfactory, developing, meets expectations, and the last one exceeds expectations. Okay, and they're just giving basic examples of how I'm supposed to grade you in this type of thing. Okay, so I'll give you guys this information too.
I guess you're gonna post this on Canvas.
Yeah, yeah, exactly.
You said you're grading these, so does this count as towards our class grade?
Oh wow. Well, here's the thing.
He's doing.
See, I'm not supposed to change the syllabus, because when you guys sign up for the course, the syllabus is like where you guys are baking your whole semester run, and that's what you're gearing up towards. And this was dropped in our lap, midway through the semester. Well, actually over midway. So it is mandatory, but it's not. But your grade does not depend on it, I would say.
Bonus? I think you should offer bonus so people take it seriously.
That's a good idea.
Because if it's not worth it, I think people aren't going to take it seriously.
Yeah. Okay. I'm okay with that. I mean, there's nothing in our syllabus that says we can't have a bonus. Right? Okay. So yeah. So if you don't do it, well, I guess so it only helps you if you do it, right? That's the thing. And also too, it also helps the university, right? Because it allows ABET to assess if you guys are actually, coming along okay and learning, this material. This material in this course is complex enough already without this, but this course is a standard for electrical engineers. Okay, so. All right, so any other questions for this before we move on? Yeah.
When's it due?
Oh, good question. So let's, wow. I believe I have until the end of the semester, which is actually even after finals. And I know you guys have other courses and other exams coming up and finals. So I'm just gonna say, get it to me before the end of the semester. Okay. Sooner the better, I think, because I think towards the end of the semester, like when you guys are done, you guys probably just want to get away and go on break. But so I'll keep hounding you about it, maybe. Yeah.
Well, so if we're gonna make it part of our grade, or like a bonus or something, should we turn it in before the final, so we can know if we need to take the final? I mean, you know what I mean? Like
Okay.
like if I end up with an 88 or whatever, and then
Oh, like if you're just like a point or two away or something like
yeah,
that.
and that pushes me up to where I don't have to take.
Well, yeah. Okay. So yeah, yeah. So if you want to turn in earlier, so you'll know. Yeah. So for those of you who turn in earlier and you want to, see what your grade is on this assignment to see how much you have to play with, yeah, go ahead and do it. That's fine. Yeah, so on the online grades that I post up online, I'll constantly update those with like, who's ever turned it in early, I'll quickly grade it and post it. Yeah. Yeah, that's a useful thing to have. Yeah, but yes, so I'm not exactly sure when grades are due, but typically they're due probably, okay, so that's Thursday. Our finals on Thursday, the 12th. So likely the grades will be due the end of that week or first thing Monday of the following week. It's probably Friday. That's what I'm guessing.
They usually choose like
Well,
Monday.
there are some exams on Friday,
Yeah.
so I don't
Oh,
know.
there's probably Monday.
It's usually like
Okay.
Monday.
Okay. Yeah, it's like shortly after finals, and we have a pretty late final. But that's good that we, don't have a. I feel sorry for people who have a final on Monday that week. They don't have very much time to study. Okay. Anything else? Yeah. Okay. Great. Okay. So for today. Maybe 15 minutes. All right, so we're going to continue on with chapter 15. For review, last time we looked at comments. Oh wait.
Hit the button on top of the receiver, turn it off.
Here.
Yeah, you got it.
Okay.
Well,
Okay. So last time we went over common source, common gate, common drain, common emitter, base, collector, and things are not useful, right? And so we found out that it's not useful if you want to use the collector or the drain as an input, because those are best used as outputs, or if you want to use the base or the gate as an output, because those are best used as inputs, right? The emitter and source, either or, so that's fine there. And here's some examples we went through, many of them. And also for the JFETs, which we encountered in this exercise right here. That's a gate, and yeah, so this right here is sort of offset. So the part that's offset tells you which part is the source, so the drain. Okay, and we also looked at ways to use bias to remove some cue point limitations dealing with the VEE voltage and the REE resistance. So this was right. So this right here was the REE resistance right here, and so we put a current source right here to deal with that, and also stabilize the operating point. And so the purpose of doing that, this has its own kind of cue point, where this right here, if you look at the ID curve, this right here is like the slope. That slope is like 1 over the resistor. I mean the resistance of that of this element right here. So this element does have some effective resistance. So we're not getting rid of the resistor. We're just replacing with something that behaves like with that type of resistance. Okay. And if you're going to do DC analysis, you replace this with a current source. If you're doing AC analysis, then you replace this with a resistor. Okay, so we'll continue on 15. Okay, so so here's a differential amplifier, right, where we split it down the middle, right, and we could look at the differential mode, where this is VID, the differential input, right, for the half circuit, or you could look at the common mode half circuit, where here's a common input right here. And you can see here it has a few differences, like this part right here is grounded, and this part right here has that resistance. Up here is the same, and yeah. And this current going here, there's like no, it has very large resistance going into this gate here, so very little current. Okay. So it says here in the differential mode half circuit, the MOSFET sources represent a virtual ground right here. That's differential mode. And in a common mode half circuit, the electronic current source has been modeled by twice its small signal output resistance right here. Okay. So remember, that's for like AC. So we would replace this with this equivalent resistance. Okay. So so let's find the differential mode gain, right? Right. So here we see that we have the VD1, VD2 given by this expression, and the VOD, which is across the difference between these two right here, is given as that. And so the differential mode gain is the VOD divided by the VID, which is the differential output and differential mode input, right? And we're evaluating it where this is 0, so we're looking at this part right here, because this contribution is 0 over there. Here's what we get for that expression. And this approximation is if your RO is much, much greater than your RD. So that would, which is probably the case a lot of times. So that's why this just gets approximated to this RD instead of RD in parallel with RO. Okay, so the differential mode input resistance is RID, the differential mode input, and that's an infinite. And that's due to very high resistance coming in here, no current. And the differential mode output resistance is this right here, but in parallel. So for the differential mode output, what you would do is replace this right here with its small signal counterpart, right? So that would be a voltage-controlled current source. So when that's replaced with that, you have this output resistance in parallel with this RD right here. And that's where that comes from. Okay, so the MOSFET differential amplifier provides improved linear input signal range and distortion characteristics over that of a single transistor, right? For instance, the drain current expression for the MOSFET is this. So these two drain currents, the difference between that is this expression right here. But then what you can do is you can replace this term and that, these two terms right here with these two things right there. And so you would have some cancellation, and you would end up with this right here. And you can clearly see that the second order product cancels, right? So this is all first order. And the output current expression is distortion free, which is nice. Okay, so the common mode half circuit is as that of an input amplifier with a source resistor of 2 RSS. And so the differential mode output voltage is 0 right here, and that's because of this right here, those two things. And the signal voltage at the source is this right here. And this approximation is assuming that these values are quite large, so this 1 becomes insignificant, and so this ratio becomes about 1, so that's just the VIC, common mode input. So the common mode conversion gain for a differential output is this, so it's just this expression right here, right? Put it in there, and then you're going to get 0 for that. The common mode gain is given by this expression right here. Oh yeah, and I should remind you guys, when we have our practice exam and our real exam coming up pretty soon, I'm going to give you guys the equation. So I'll probably give you guys a table for this kind of stuff, because we have lots of formulations and lots of approximations that we make from these things. Okay, but you guys will have that. But it'd be important to know how to use them though. Since the common mode input source is connected directly to the MOSFET gate, the input current is 0. Thus, the common mode input resistance is this right here, infinite. For a purely common mode input signal, the output voltage of the balanced MOS differential amplifier is 0, and the common mode rejection ratio is infinite. And just to remind you guys what this common mode is, remember before, I think it was back in chapter 11, we first encountered the common mode rejection ratio. So you have this differential input and this common mode input right here. And so the common mode rejection ratio was underneath this expression right here. So what you want to do is you'd like to eliminate this or reject that. So this value right here should be quite large. So you would want to get this as large as you can. So this quantity right here would be small. So your output is just related to your amplitude times your differential input. Okay, so that's the goal. And so for your common mode rejection ratio, you can it'll be expressed like this. And then so what you'd want to do is try to maximize your RSS value, and you can do that directly, or you can use your bias current right here to do that. So a couple of ways of increasing that value. Okay, so now let's get into the evolution of the basic operational amplifier from our transistors analysis. So one important application of the differential amplifier is at the input stage of the operational amplifier. This is because the differential amplifier provides desired differential input and it rejects the common mode. However, the op-amp usually requires higher voltage gain than is available from a single differential amplifier stage, and most op-amps use at least 2 stages of gain. Now, there is a third stage, but that third stage is for the output, and that is to provide a low resistance and high output current. Okay, so here's example of this. So here's a 2-stage prototype for op-amp right here. So here's your op-amp. As you can see here, there's 3 transistors right here, bipolar. And here's the DC equivalent. And you can see here the difference is that instead of having your voltage inputs, both of these are grounded right there. And also, since it is a DC equivalent circuit, your bias current is replaced with just a regular current source. Okay? And since those are grounded, you see that's grounded also in the picture right there too. And also, this voltage right here is 0. So to achieve a higher gain, a PNP common emitter amplifier Q3 has been connected to the output of a differential amplifier, this Q1 and Q2, those two. to form a simple two-stage op-amp. Bias is provided by the current source, I1, right here, and the positions of inputs V1 and V2 have been reversed to account for the additional phase inversion by Q3. So that's why for Q1, you have this voltage over here, this V1, and you have this over here for V2. Okay, so those two things are reversed for that reason. Okay, so let's do DC analysis, we'll end with the DC analysis today, but we'll pick up on Friday with AC analysis and also the common mode rejection ratio. So for DC analysis, so let's use the DC equivalent circuit to find the Q points of the 3 transistors. So the emitter currents for Q1 and Q2, right here, those are each equal to 1/2 of the bias current. Okay, so here's the bias current right here of this I1. And so these two currents coming out of here are each 1/2 of that. They're balanced and equal. The voltage at the collectors of Q1 and Q2 are this right here. So this VC1 and VC2, those are right there. And so that's just equal to VCC at the top minus IC1 times this RC. That's the voltage drop going across here in both of those cases. However, on this one right here, we do have this current coming off of this right here, right? Coming off of the base, that IB3. So the current going down this path right here is actually the combination of these two currents right here. You have your IC2 minus your IB3. Your IC2 and your IB3 coming in here. That's the current going through here. Okay, so if the base current IB3 of this Q3 is neglected, then we just have this. So then your two voltages would be equal, or about equal, and it would just be equal to your VCC minus your I1, well, half of your I1 times your RC. Okay. So continuing on from this right here, since this VE is equal to negative BE right here, and that's your VE right here, and these two expressions, your VCE1 is about equal to VCE2, which is equal to this expression, and that's including this VBE right here. The voltage drop across RC is constrained to be about equal to the emitter base voltage right here of your Q3 are approximately 0.7 volts. So it looks like what they're trying to do is constrain a few things. Not only that, but you're also it also constrains what you can choose for your RC as well. So since you want this voltage to be constrained to be 0 right here, then that means your IC3, it must satisfy this right here, and also this must be satisfied. And lastly, right here, the quantities EB3 and IC3 are related through the BJT model, which is this right here, where this IS3 is a saturation current of your Q3 transistor. And for your offset voltage of the amplifier to be 0, right here, the value of RC must be selected to satisfy this. So here's that constraint I was talking about. Yeah, so like I said, it is a little bit complicated, lots of equations, but for the analysis that we'll do for, I will provide the equations for you guys, okay, and also give you guys hints. Okay, so that's it for today. See you guys on Friday.